Okay, hashing. You guys should say hashing once in an algorithms class. So this is that one time. And besides, hash tables like you might expect, I'm going to give a fun application to heavy hitters, which will give a different perspective on hashing, which rumor is you might have seen before. Okay, so here we go. All right, so we're still doing randomized algorithms as part of this average, pseudo average analysis of algorithms. Again, we're only averaging over random bits. We're not going to lose the whole worst case over inputs, which is really the most important thing. And right, so okay, so first things first, we'll talk about hash function and hash tables. All right, so who's seen this web page before? Like a million times? Maybe you haven't? Yeah, this seems to be, at least when I made it, maybe it's a couple years old, which is like half your lifetime. Um, but this was supposed to be a documentation page for just Python dictionaries, right? So in Python, this is just provided by default, where you have these objects, you just set key values for free. Probably never thought about how they work because they seem to work just fine. Uh, in a previous era, like when I was your age, we had to deal with this website. Anyone seen this website before? Okay, so there you have to deal with, these interfaces. So everything is typed in a key value fashion, and uh, and somehow it's like way more painful to do the equally simple thing. But these are both, examples of dictionaries or maps or whatever. And these are just like the most important objects ever in practice, right? Like, I don't know if, like, do you guys know how like the object system in Python is implemented? It's just like dictionaries with parent dictionaries for default, but like it's just dictionaries all the way down. And then like I feel like we're all taught that we're supposed to do some kind of like object-oriented programming where all the types are planned out way ahead of time and you do some beautiful design. But like anyone who's worked knows that like within 2 weeks you're just passing around like massive property hash maps around and you're no longer doing clever objects and you just throw everything into a hash map and you just keep going. Of course, that's completely embraced by Python. Okay, good. So all right, so maybe I should at least mention dictionaries. You can insert key value, delete a key, look up the value for a key. That's all you want to implement. Okay, a very special case that sort of comes up implicitly for us all the time, okay, is when all the keys are a fixed integer between 1 and n is known ahead of time, right? At some level, every time we did one of these like graph problems, I give you a graph or whatever, even if it didn't quite come like this originally, you could have taken a graph and the first thing you do is number all the vertices. And now everything's between 1 and n. And for the rest of your algorithm, you have this automatic lookup. Oh, that's vertex 5. I go to slot 5. Okay, so lots of problems actually just look like this. Now, for this kind of situation, if you want to implement a dictionary, what should you do? Just use an array, right? Array is perfect. Constant access, no memory overhead. If you know what you need ahead of time, it's ideal. Okay, so arrays are great, especially in static settings where things are fixed. But when is it not so good? Yeah, big, sparse, and also situations where like things are more dynamic when keys are changing. Okay. So, uh, our more general problem uh, is going to be n integers out of some much larger universe. Okay, effectively unbounded as far as we're concerned. Um, so I guess the example I give here is that you can encode any string as a super large number, by just writing out the ASCII. The first letter is the least significant digit, the second letter is the second least significant digit, I guess going backwards. Right. So you can encode, these. Why does it keep saying this? Uh, you can encode, uh, strings as massive numbers. Those are your keys, right? So that's not going to fit in any like dense listing from 1 to n. You're in this much bigger space of basically all possible words. Okay, so um, so in this kind of situation, uh, an array would still take constant time, which is perfect, right? And the only issue is that the space is proportional to the space of possible keys and not proportional to space of actual keys. This, of course, you already knew. Okay, so the second idea then is something like a self-balanced tree. Okay, how much space would a self-balanced tree or some other smart binary tree take for n keys? N. And about how much time per operation? Yeah, log n, maybe amortized. Okay, so we have a situation that looks kind of like this. So arrays will get you constant time, super fast, but the space may be very poor. Okay. For a search tree, the space is going to be really tight. It's going to be big O of n because every node will contain some useful data. But your search time, because you have to compare all these things, is going to look like log n. So the question is, can you get the best of both worlds? And the answer is, huh? Sorta. Okay, I just wrote yes with randomization. Okay, so uh, you're going to try to get constant time, constant space, uh, which is like, sounds too good to be true, and you can get away with it if you use randomization. Good. All right, so the main kind of randomization we're going to use today are hash functions, which I'm sure you've heard of before. So a hash function is going to just be a map from integer to integers, usually mapping from a very large range of integers to a smaller range of integers. Okay, so n should be considered relatively big, k should be relatively small. I'm going to apologize right now. I think I'm very inconsistent about using n's and k's throughout different slides. So, but in this slide, n is the bigger one, k is the smaller one. And so what's the idea? You have this n possible slots, and you're going to compute some kind of map into k smaller, a smaller array of k slots, right? So everything is going to get mapped in, uh, something like this. Okay. Uh, Now, what's one issue that comes up when I map many things to one thing to a smaller space? You're going to get conflicts, right? If I have 100 things mapping into 20, each slot down below will on average have 5. So these are called collisions. Okay, so the real question is, how do we deal with collisions? Okay, now there's many, of course, different ways to generate a map from n numbers to k numbers. Um, What you probably first have in mind is a uniformly random function. Each input could go anywhere in the output, right? So that's called an ideal hash function, which I think is a good name for it. So this is a uniformly random map from the big space to a smaller one, okay? And often when you're designing everything we do subsequently, that's a fine model to keep in mind, right? You're trying to think of how to take advantage of randomness. Okay, I imagine everything goes everywhere. That's easier to think through. Okay, but there are some practical issues with ideal hash functions. What is a practical issue with an ideal hash function? Suppose you have access to randomness, and we're not going to get into a philosophical debate about whether real randomness exists. Uh, Besides that point, yeah, space. So how much space would you need to write down an ideal hash function? You can actually give a very precise answer to this. Or what's one way to write down a ideal hash function? Yeah, you can just build out the table, right? Oh, this goes here, that goes here. That would take like n space or n log k because you need log k bits for each. The question is, can you do better? Can you do better than n log k? If yes, how? If no, why not? We can take a vote. We haven't voted in a while. Okay. So you got some choices? Yes. Smaller. You can do smaller. No. No smaller, I guess. N log k is best you can do. I mean, a table is basically all you can do. Or not voting. Okay. Who's not voting? Okay. All right. Who thinks that you can do better? Something smaller. Yeah, yeah. So an ideal hash function, the question is how much space do you need to write it down? One option is for every one of your inputs, you just write down where it goes. That would take n log k because you need log k for each of the outputs. The question is, can you do better? Yes means better. No means no, not better. And then not voting means, yeah, not voting. So do you want to not vote? Because it's the only thing we've. Yeah. You vote. Okay, so who's voting yes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. Okay. Who's voting no? 1, 2, 3, 4. Did you vote? You vote yes. Okay. 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. That's amazing. Every vote we've had, everyone has either. Yeah, that's. There's like this one joke I use every year. I've never had the chance to use it. Okay. Um, no, it's not about abstaining. I'm not gonna. No. Okay. Those who said yes, do you have any ideas? 9 of you said yes. Remember, you need to be able to express any possible function from n to k. Well, yeah, because we're talking about specifically about ideal hash functions. The question is not whether there's some function from n to k that could be smaller. Sure, the constant function will take no space at all. The question is, can we find a way to be able to write, say you want to use an ideal hash function because that's the nicest thing to use algorithmically. But how would you store it on the computer? Can you expect to store it any better than just writing out the whole table? Okay, some of you said no. Who said no and why? Yeah, you can't? You can't. Yeah, so why not? Oh, okay. Okay, any other? Okay. If you do this ideal hash function thing where you generate uniformly random one, how many possible functions could you generate? Okay, so there's k to the n possible, right? And so you need to be able to write down k to the n different things. So how many bits do you need? The log of that, right? Because every bit string needs to distinguish a different one of these tables. So just taking logs tells you you actually need n log k space. Okay. Which remember, if we're uh, well done. And when n is ginormous, right, like the size of the universe, that's not practical anymore. I mean, I guess you could generate random numbers as needed, but yeah. Okay. So what we kind of want to do, the real thing about hash functions is trying to sort of replicate or simulate a uniformly random thing, but it's got to be somehow much more compact. Yeah. So today I think this will suffice. It's sort of like a bare minimum. So if I had an ideal hash function, any two keys, the odds of them colliding should be 1 over k, right? Because you place the first one somewhere, one out of the k slots, and the next one has any chance of being anyone, including colliding. Right? So it should collide with probability 1 over k. That feels like a bare minimum for any reasonable hash function. So universal hash function is this bare minimum. It doesn't say anything about the whole distribution of keys being very uniform, but it say any two keys, the odds of them colliding should be as if it were ideal, 1 in k. Okay. So that's the idea. Any ideas for how to generate one? It's hard to guess, but maybe it's still a fun exercise. No, because this needs to hold for all pairs I and j. Yeah, and to be clear about the randomness, so h is a function that you randomly construct once. That makes sense. So that probability is kind of over the randomized construction. Pick ij ahead of time, you create some function h, then you check. Okay, so the function we're going to look at has the following very simple form. Just ax plus b mod p mod k. There's a little bit of subtlety here. So first, p is a prime number, something bigger than k. A is chosen uniformly at random between 1 and p, and b is chosen uniformly at random between 0 and p minus 1. And like in the randomized class, this might be on the homework, second homework or something to work through, showing this is pairwise independent. Um, good. So, okay, so that's just relatively simple. So I think that the main thing to point out though is that p is going to be pretty close to k. So the number of bits you need for p should be roughly log k. And then a and b will also both need about uh, log k bits. Okay, so you're only looking at storing 3 numbers instead of storing n of them. Okay, good. And this is enough to get 1 over k. I won't prove that here, but you know, it's not that bad. It's just a little grungy, and the steps are in the exercise. Okay, good. So now we'll talk about hashing and hash tables. So what we're going to do, again, here I'm being a little bit inconsistent about notation. So I have a very large universe of size u, and then we're hashing into a smaller array of size m, and there's n keys, right? But the idea is I'm just going to generate a pairwise independent hash function, at least in this first pass, and use that to find a slot in the smaller array. Okay, and the main issue for us, the only real design question is inevitably keys are going to collide because you're going from a big space to a small space. And so the question is, how do you deal with these collisions? It'd be great if they all had their own slot, but maybe that's not the case. Okay. So I left a blank slate for us. All right, because you might have heard of some stuff or you might think of some stuff. What are some ways to handle collisions? Okay, probing. Uh, what's probing? Okay, so I have a picture coming up, but yeah, probing is like searching the array for the next empty slot. It's called linear probing sometimes. Okay, other ideas? Okay, so down here, I can have a secondary data structure. It can be a tree. I could also even just do a linked list. You're hoping maybe it's so small down there that a sophisticated data structure might not be necessary. Other ideas? You can just make m bigger and bigger. Oh, okay, I got a conflict, panic, double, right? Other idea? Huh? Yeah, even this data structure, whatever data structure we put down here, could be yet another hash table. Right? Other ideas? Just for fun. All right, I have a list. Oh, chaining. Chaining sometimes well, if I'm on the same page, refers to this thing where we make a linked list down below. So, okay, so here's some things I wrote down. Yeah, make the array bigger and bigger. Chaining, which is making a linked list for all the collisions. Well, let me come back to cuckoo hashing. Linear probing is down here. If you go to a slot and it's occupied, just keep going until you find an empty slot, put it there. That means on lookup, you're going to go in and you're going to find your thing occupied with a different key, and you have to keep going until you either find your key or you find an empty slot. Okay. If we have time, I have linear probing loaded up at the end, but I'm not sure. That's often a lecture in the randomized class. The cuckoo hashing is kind of fun. So cuckoo hashing, you create two hash functions, and you hash a key, and if it's already occupied, there's a couple of different approaches. So say it's occupied by a key, and I'll take this key and say, well, I'm going to put you in your other hash. And if there's another conflict, you'll get bumped and bumped and bumped and bumped. And apparently, cuckoo birds actually like do this to each other or something. Like they like take over each other's nests and knock out each other's eggs or something. Anyway, but you have two hash functions. They sort of you try to resolve the conflict by bumping each other out. And so if you really can't get things to work, then you must have like something that looks like a massive cycle where you keep bumping, 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 and get back, you still can't find a slot. Kind of thing. That's how you analyze it. So that's kind of fun. And there's many more. There's like a whole field of exotic hash tables out there. Is there something called quadratic probe? I don't think it's a thing. Oh, well, no. I mean, I never took 251. I may be ignorant. Uh, or maybe not. I don't know. What was quadratic probe? Did you? Oh, okay. I'm not totally sure if it's going to help much in the worst case if you use appropriate hash functions. If you did linear probing correctly. Um, so I should mention linear probing might do the best in practice because you hit the array and then you scan the array. And that's just going to be very hardware friendly because it's already loaded into cache and things like this. Um, it's also one of the earliest algorithms to be analyzed. So vacuum, when you straight up using vacuum tubes or something, this is the only one you can implement. Like you're not going to do linked lists, and stuff like that. You're just going to scan down the array. And so Donald Knuth analyzed this in like the 50s or something. And so it might be arguably like the first rigorously analyzed algorithm to some extent, because not many people were doing this kind of thing back then. Um, okay, so yes, but as I understand, linear probing is the most practical. Okay, so but we're going to analyze chaining as sort of our warm-up example. If we have time, we could do the more sophisticated linear probing, but we have heavy hitters in the middle. Okay, so that could also be a topic next week if you wanted that. All right, so chaining universal hash functions. So what's the idea? You have these n keys, and the first thing you're going to do is do your ax plus b mod p. So that's some like secondary. You can think of it as like a secondary table, and then you're going to take that and you're going to do your mod m, and you're going to make a linked list whenever there's conflicts. Okay, so that's, I don't know, me trying to draw a picture for an equation. All right, so this is going to be pretty simple. So there's n keys, okay, and your smaller table below has space m. Okay? The claim is that each of your insertions and lookups and deletions, an expectation is to take like n over m time. Okay? So the question is, Why? Or even just how do we start? How do we go about it? Because we've never done something like this before. Okay, so how do I articulate this? So maybe I might write first fix a key. Okay. Now the running time is going to be what? I hash and then I scan the linked list, right? So the running time, so fix key K. So the running time is going to be proportional, that's a symbol, to, like the number of conflicts, because that's how big the, or number of collisions is probably the better word. That's how long the linked list will be. Okay. So now we just have to figure out how many other keys we expect to collide. Okay. So the expected number of collisions. Yeah. So how should I set this up? This is partly just a, practicing. How do I write this down? Even if intuitively this is all going to make a lot of sense. Yeah. Oh, okay. Okay, summing over all I times the probability that there's I collisions. Okay. So I guess we have to figure out what's the probability that there's I collisions. To be clear, we're using a universal hash function. Oh, okay. Can I so that other approach, this suggestion might be something like summing over all I from 1 to m, where m is the number of slots in a smaller array. So I guess it's the probability that first hk, first you need to know that hk gets mapped to I, times, I guess, probably the expected number of keys L that also get mapped, oops, that also get mapped to I, given, you have to be a little bit careful here, because you're already assuming that HK is going to I, and assuming that how many other things go to I. Okay. Oh, okay. So one sec. So instead, can you do what? Between I and J less than. Oh, so something like we did for quicksort. So Xij is equal to, be a random variable. It should be some quantity, and the quantity reflects what? It's J, which I should write out as Hi is equal to Hj, 0 otherwise. So that means that the number of collisions will be summing up all the keys other than I. I think not necessarily the ones that are just less than. So I'll write J is not equal to I. So any other key J, I'll write key. Uh, oh, I guess we're using, oh wait, what do you mean I collides? Do you mean K? Like usually the keys collide. And I was using K for that key, and J will refer to another key then. So I'm looking at all keys J that are not equal to K. Sorry for the bad handwriting. X, I'll make this K. XKJ. So I'm summing up over all other keys, this thing that's a 1 if they collided, 0 if they didn't collide. So that'll give me the total number of collisions. Yeah? And then I want to analyze this thing. So what should I do? Analytically, or what are we looking for? Put some expectations around this, right? And what's the only buzzword? Yeah, we can do linear of expectation. It's exciting, like that. Okay. And now what is this? Now I just have to analyze two. One of these terms is just two keys. What are the odds of them colliding? Uh, this is where my notation gets a little bit annoying. There's m possible slots, and we're using universal hash function. So, so it should be 1 over m. So total number of keys, that's n, over m. Okay. So what's the key point? So I think that really the key point is how we're able to get away with using universal hash functions. So again, slight change in notation because k is in the denominator there. But all I know about the hash function is that any two have a limited chance of colliding. Otherwise, the hash function we use itself is not that random. It's just ax plus b, right? So that there's only a certain number of configurations that can take on, but it's enough to guarantee this sort of pairwise randomness. And if you look at things just the right way, in hindsight, it's not too complicated. But going forward, you have to look at just the right way. And if you look at it sideways in the right way, this pairwise independence is all we really needed for this critical step here. Okay. So this is how hash functions are able to get so efficient using such simple functions. If you look at it the right way, then you don't need that much randomness. If you're doing expectation, you don't need that much randomness. You just need to pick three random numbers, A, B. P is not random actually, so just A and B have to be random. And that's enough. Okay, so that's very practical. Okay, any questions? Okay. Maybe I'll briefly mention that linear probing needs to use let's see if I get this correctly, a five-wise independent hash function, which is sort of like saying any five keys will look as if they're uniformly randomly distributed, for what it's worth. So you need slightly stronger hash functions for linear probing, but linear probing will get a stronger guarantee where the thing will still be good in expectation, but it'll also be good, I think, with higher probability. Actually, let me take that back. But anyway, I only mentioned that there's sort of there's levels of hash functions. In some cases, require stronger ones. Hash functions Yeah. So this pairwise-ish looking one with just ax plus b. So for 3, you would do a squared x plus, sorry, ax squared plus bx plus c. You just do a quadratic, bigger polynomial equal to the independence you're going for. That's one way to do it. Yeah. So H is not necessarily uniformly random. A particular key is not promised to be, could be anywhere. All your promise is stuff related to the pairwise collisions. That's all you needed. Yeah, so you have to pay like a little bit of attention to the algorithm so you figure out just how much out randomness you need, and then the two together get you a compelling result. Yeah. I mean, it seems simple, like the algorithm is very simple, it's just a simple equation, but of course, this is like the engine behind basically everything in practice, right? Yeah. Uh, Maybe B will guarantee the more B maybe will just guarantee the uniformly random part then. Uh, uh, Reasonable question I don't have a great answer for. Uh, why do you need to be? Well, maybe the best answer is to do this exercise in the back and then you'll learn. X plus A probably wouldn't be good, right? Because everyone just gets shifted to the left by the same amount. So so you want to have no coefficient in front of A, in front of X? Because then if two things are the same mod P, then you're just getting shifted. They're going to keep conflicting. Yeah, so it's for any two keys, right? So there's still some worst case stuff. Why B? I don't know. I mean, it made more sense when I went through the steps to prove it. I have a little, maybe that's it. Yeah, you could also think of like doing A times X plus B, and I think it would have a similar effect. So that's sort of shifting X randomly before starting. Okay. Um, yeah, I think you need to have at least two. I would think it's provably impossible. I don't know. The question is, what can you do as only one variable? So, well, I guess one thing you know is that if you only have one variable, then you're only generating a limited number of functions. That might be enough to prove that if you can only choose from one of 100 functions, there's no way you can make it pairwise independent over 100 keys or something. Yeah. But I haven't thought deeply about it. They might be Googleable. Okay, other questions. Okay. All right. So the next part we'll do a slightly different tact. Uh, so I don't know if you guys have seen this webpage before. It's sort of changed over time. But Google maintains a website called Google Trends. Um, and I actually updated this morning. So apparently these are what's been trending over the past week. You might understand some of these topics better than me. Oh, there was? Oh, it wasn't because of March Madness? Oh, bummer. Okay. Oh, was that today? Because it did say it started 2 hours ago. Okay, I didn't check the news today. Okay. Uh, there's a shooting at FSU. Okay. Uh, okay, on a lighter note, the next line is Katy Perry in space. Uh, because she went to space a couple days ago, in Jeff Bezos's rocket, I guess. And everyone's yeah, why is 4chan on the list? Glad I'm not on that list. Um, how about Nikki Cat? I like Dazed and Have you guys seen Dazed and Confused? Of course you haven't seen Dazed and Confused because Ben Affleck's in that movie. You don't know who Ben Affleck is. Huh? Oh, you've seen Dazed okay. Yeah, yeah, yeah. Okay, there you go. I don't think I should quote that movie on tape. Yeah, yeah. All right, right, right. Yeah, I don't think I can quote that movie in class without getting fired. Um, what about Nico Iamaleava? You guys know who that is? Yeah, there's some hints there. No, he left University of Tennessee. He entered up what they call a portal because now college players are basically like professional athletes. They could jump around. I guess he's going to UCLA. Although I think one thing that's sort of suspect is that his name literally says "I am going to leave." So like, uh, I don't really know what's going on with. Diabetes mellitus. Maybe I should. What is that? Oh, what was she in? Yeah, but who is she? Okay. Yeah, I don't know. I don't know what DH gate is. Um, Carmelo Anthony case, which apparently is not the basketball player Carmelo Anthony. Yeah, but that's not how you spell Carmelo Anthony, the one I'm used to. But it's a different Carmelo Anthony. Wait, is that the New York Knicks Carmelo Anthony? Oh, okay. This is a very bleak. Because the next guy is the guy who's stuck in El Salvador, I think. What about Oblivion? That's some video game you guys play, right? Okay. All right. I guess it's been worse. Like when I made these slides during COVID, it was probably more bleak. Okay. Um, oh yeah, that was the one historically. Yeah, that happened like roughly the day Jeff Holmgren tore his ACL. Anyone know who Chet Holmgren is? Okay. Um, all right. So, okay. So they don't just do this for fun. They're tracking the most popular trends because they're saving everything, right? Why is Google so fast? Because when you ask your beloved question, a million of other people already asked your beloved question and they just reserve it. Okay, they're not searching the whole internet in zero time, right? So what they want to do is they want to figure out what's trending and just cache it so they don't have to redo all this stuff, right? So caching is just everywhere in practice. It's all over the place. But the question is how? Right? It's a challenging question because there's so many possible things that could be trending, right? There's like basically an infinite number of keys, right? So what makes this sort of interesting is that there's way too many potential queries to be able to sorry, to be able to maintain a counter for every single one. Okay? So the question is, how do you do this in sort of this in this setting where you're trying to keep count of something that's actually bigger than you can keep count of? Okay. Okay, so we're gonna model this in the streaming model. Have you seen this before? So this is abstracted a little bit, but the idea is that we're gonna have elements that appear one at a time, right? So maybe the first one is the letter A, and then B, and then C, right? And these will come through your computer one at a time. Okay, something like this. And Uh, and so as these elements pass through, you want to say figure out all the elements that appear at least 5% of the time. Okay. And yeah, maybe one way to think about this though is that your computer is going to have very limited space. Okay, so maybe this is like your computer. And the idea is that the size of your computer is going to be way smaller than the entire input. So it's not like you can just gobble everything up and count everything. So you're only going to be able to keep space that's proportional to basically a few items at a time. They'll pass through your computer. You need to update your state, and then you throw it out. You don't get to revisit this information. It's like a stream of water. Once the water passes through, it's gone. Okay. So our goal is to try to identify all the heavy hitters in space that's like sublinear in the number of possible keys, right? Like if there's n possible keys, you can get down to square root n. That would already be a win. Maybe you can get down to log n, maybe something in between, maybe a constant. Who knows, right? But our goal is to make be able to do something in much smaller space than keeping track of all the counters. Yeah. So if it was like 5%, it's any element that appears at least 5% of the time. But in general, that's going to be some parameter epsilon. Yeah, that'll be like IDs. Sure. Yeah. I mean, the highest order bit is trying to get down the dependence on n, because n is just dominating. Epsilon will be something modest, 1%. Even 1 in a million could be very small compared to, I mean, very modest compared to how many possible terms there are. Yeah, you get to see the whole stream. But what's tricky, right, is that you don't know which ones are gonna be the heavy hitters, and you can't keep track of all these counters for everyone, right? So you don't know what's gonna be the heavy hitter. And we're doing this in some worst case thing. We're not assuming you can, like, make a statistical model and just guess what's gonna be trending. Right. Okay, good. So, uh, right. So, on the face of it, this should seem impossible because there's n possible things to keep track of, and you're trying to say something, kinda precise about it, okay? But there's a few things we're gonna do that makes this even plausible, right? Because if I ask you to maintain a count for every single possible query, there's nothing you can do besides keeping a count for every possible query, right? But what about there's some aspects about this problem that might make it a little bit easier. Does anyone have a glimmer of hope for this problem? Number of what? Number of terms. What about it? There's a huge number of possible terms. Well, even if you only kept an epsilon fraction, you just sampled an epsilon fraction of the stream, you still have epsilon times n, something proportional to n. Okay, there's a couple of things. So one is that, well, you're trying to figure out the heavy hitters, say 5%. One good thing is that there's only at most 20 of them, right? Because each of them represents 5% of the stream. If I was looking for 1% heavy hitters, there's only 100. So the input's huge, but sort of the output is at least modest. So if we can get something that's proportional to the output size, that would be good. I mean, if this wasn't the case and you had to potentially output a gazillion names, it seems impossible to do anything better than remembering all gazillion at some level, right? The fact that you only have the output, the target output is small gives us some hope. Okay. Now, two other things that are going to help us. One, we're going to use randomization. The algorithm will be allowed to fail with some small, very small probability. And we'll be able to drive that probability really down fast, but it doesn't have to be perfect. And that might let us cut some corners. And two is we are going to allow some margin of error. Okay. Uh, and I guess I'll explain that in a moment. I guess at some level, we're going to do something like this. Let's say I want to get like 10% heavy hitters. And what I'm going to do is I'm going to ask you to output a list that, say, includes all the 10% heavy hitters. It might also include things that are at least 5% heavy hitters. So you have a few extra, but they're still pretty good. So I'll allow a small margin of error, but you still have to contain all the 10% heavy hitters. Okay. And one point I want to make, although this relaxes the problem a little bit, we're still not giving up on rigor. We will analyze the probability of error. We will be very specific about what we mean by approximation. It'll be quantified, and it'll still work on any input. Okay, good. Which is, of course, a very standard style of thinking, maybe like beyond this class. When you start wanting to do things that you can't do as cleanly as we've been doing all semester, then you have to start making some compromises, but you still want to be careful and disciplined about it. Okay, good. Interlude for Markov's inequality, but we already did this a couple of times ago. At most half the population can make twice the average national income. At most half of the NBA players can score twice the league average points. Half the students can get twice the midterm average. Okay. Okay, so let's go back to heavy hitters. So again, I'm going to use this parameter epsilon for now on. I want to get epsilon heavy hitters, anything that appears at least an epsilon fraction at a time. And we're going to formulate the problem a little bit differently. Instead of focusing too much on gathering the heavy hitters, I'm going to try to get an estimate on the relative frequency for every element. Okay. And afterwards, you can kind of go through and look through your table and figure out the heavy hitters. It's a homework problem to turn it into the original thing. So let me define this carefully. The absolute frequency of an element will be exactly the absolute number of times it appears. The relative frequency is the number of times divided by the total length of the stream. So that's looks more like a percent. And we're going to try to figure out how to estimate the relative frequency up to some fixed error for every single element. Yeah, give you like an error of 1%, epsilon is 0.01. Can you maintain for every single number some estimate that's off by at most 0.01? Yeah. Good. All right. So you want to estimate all the relative frequencies up to epsilon additive error. So the relative frequency is some number between 0 and 1, right? And you can be off by epsilon. But of course, you don't have space to maintain all the counters. What's the saving grace? So we are going to maintain an estimate for every single number or every single element. Of course, I don't have room for all of that to do it exactly. So what's one observation that gives us some hope? Yeah. Um, we will do something like that, but that's not, well, that wasn't quite about what I'm looking for. So right now, I'm simply worried about the fact that there's so many elements. How can I have a counter for each one? For most of them, 0 is a very good estimate, right? Because only 1 over epsilon can appear even an epsilon fraction at a time. So if you had 0 for most of them, that would actually potentially fit in small space. Right? So if you can, for example, keep track of the IDs and the values of just the heavy ones, then you'd be okay. It's not exactly what we'll do, but good. Of course, the catch is we don't know which of the 1 over epsilon elements we need to count. Okay, so there are a limited number of counters we actually need because for the rest of them, 0 is just fine. The only issue is, as that stream comes in online, you don't know which ones are the important ones. And you can't just sample the beginning of the stream because maybe they're all coming at the end or something like this. It's an adversarial stream. Okay. All right. Any ideas before I? Yeah. So any ideas how to use hashing? Oh, you've seen this before. K hash functions. Okay. So we're going to use multiple hash functions in what fashion? Okay. Any ideas for how to use hash functions? It'll kind of look like a hash table, but of course, that's not exactly what we're doing. Yeah. Store what in the first row? Then you're gonna have a bunch of keys listed. Ah, but then we're basically building a hash table. So we're still storing all the keys. That we don't quite want to do. Yeah, yeah, but you're still making a list of all the keys you've ever seen, right? Yeah, that's basically a hash table like we just did. Yeah. Maybe it sounds like, did you have another idea before I reveal the next slide? Or somebody over here? No. Okay. Okay, so maybe this is what you had in mind. So basically, like, I know I need something like 1 over epsilon counters. I'll make a couple extra. I'll make 10 over epsilon counters. And I'm basically going to assign all the elements randomly to counters using a hash function. Okay. So something like this. So if element I comes in, I hash it to the appropriate counter and I increment that counter. Okay. So one of these, right? This thing is going to be the sum of the counts of everything that hashed to it, right? So maybe it's x plus y in this picture. Okay. So we're going to hash down, and each counter is going to represent a sum over everything that hashed to it. Okay. It makes some sense. You're hoping, for example, that your heavy hitters are kind of separated from each other and they get their own counters. That's why we allocate a few extra. And maybe the other ones don't make too big a difference or something. Yeah, good. All right. So I left this for you guys to fill in. So imagine I have this algorithm where I'm going through the stream and I see an element and I hash down, I increase the counter, hash, hash. How would I now, suppose I say, oh, here's element 100. What's the estimate? What would you estimate for a frequency? Hash and just check the counter. Right now we only have one row. So you're just going to return, yeah, I should say A of HI. Okay, which might overcount the frequency because it includes counts from some other elements. Okay, good. So now we just have to analyze this thing. Here's some notation. I'll use A to be our array of counters. Fi will be the true frequency of I. H will be our universal hash function. M is the length of the stream. Okay, so Aj is summing up all the frequencies that got hashed in slot J. Okay, good. Okay, so here's our main lemma actually. So for any particular key I, there's probably at least one half. I'll return an estimate that's at least the true frequency, and at most the frequency plus epsilon over 5 times the total stream, length of the stream. The total number of elements is repetition, so the length of the stream. Okay, so first of all, this inequality is more straightforward. Why is this one true? Yeah, I mean, that counter is just overcounting because it might get some extra things, but it definitely includes everything from I. So the real question is this. How do we prove this? Okay. All right, how should we analyze this? What's a reasonable first step? Yeah, that will kind of do. Well, okay, so maybe we want to study this quantity, right? This is what we're interested in, the counter. And so what should I ask about it? Uh-huh. You can subtract too, but I want to say something about it in particular. Because, for example, that quantity is going to be different over different random runs, right? Yeah, let's start with the expected value. Okay. All right. So how do I analyze expected value? Yeah, we can sum over do linear of expectation. So like a sum over all keys j. Uh, okay, so it's going to be linear expectation. I'm kind of skipping a step. But you're going to say, okay, the probability that hj is equal to hi times fj, right? This is the expectation of one other key's contribution. Okay, and so there's a linear expectation going on there, although it's a little hard to see. Okay, good. Great. So we break it down into all these keys, right? And now what? Right. So now because it's a universal hash function, the odds of it colliding should be inversely proportional to the size of your array. So then you're summing something like over j, epsilon over 10, because I had 10 over epsilon slots, fj. Is that correct? There's one key that has to be distinguished. Yeah, itself. So this sum is only over the other keys, plus you have f of I. Okay, good. And what does this all sum up to? Yeah, you can round it up to m. So you'll get epsilon over 10 times m. It's really m minus fi, but it's not very significant. Okay, good. So the expected value is at most a frequency plus like an epsilon over 10 fraction of everything else. That makes total sense, right? So I have a counter going in, and the rest is just noise. But the universal hash function is sort of saying that on average, the noise gets spread evenly, and you only get your own proportional fraction of the noise, epsilon over 10. Okay, so the expected value looks a bit like our inequality that we're going for. But now I want to say something a little bit qualitatively different. I want to say the probability of getting twice that error, epsilon over 5m, is at most 1/2. Okay, what do I use Markov's inequality on? You're going to use Markov's inequality. So Markov's inequality says, the probability of getting twice the average is at most 1/2. The variable has to be non-negative. Well, what's the variable? Okay, so this part's subtle. So we're going to apply Markov's inequality, but we're going to actually apply it to minus fi greater than equal to epsilon over 5m. Okay? And here it's really important to point out that we're always overcounting. So that left-hand side is always non-negative. Markov's inequality only works for non-negative random variables because it's really a packing argument. Okay? So what we just showed is that this is the right-hand side represents at least twice the average. Minus fi is at least 2 times the expected value of, well, I'm running out of space, this thing. Okay? Imagine I wrote it correctly inside. But it's really saying, oh, what's the odds of it being twice of its average? And that's at most 1/2. Okay, so the right-hand side is really saying the noise it gets, which is always non-negative, is at least twice the expectation at most half the time, which is actually straightforward. Okay, good. Good. All right. So we've done something good already. I've used a really small amount of space, 10 over epsilon. And now for any particular element, I'm going to get a pretty good estimate, epsilon over 5 relative error, half the time. Right? We're making some progress for a task that might have seemed impossible initially. Okay. Now I want to try to amplify this. I want to try to guarantee that I have a good estimate for all of the elements. Any ideas? Okay, we can make a bunch of copies. Okay, so let me first go through this. Okay, suppose you repeatedly flip coins. What are the odds that the first coin toss is tails? What about the first two? The first 100? Okay, I think this is what you said. Okay, all right. So what we're gonna do is we're gonna make d copies. Okay, so it's just for some parameter d we'll pick in a moment. Okay, and I'll repeat this experiment. So each copy gets a new hash function. And now how would I estimate fi? So I say, oh, here's my element I. What's the frequency? So take the average. So you can take the average. Why the min? They're all so average is totally sensible. In some cases, it's the only thing you can do. But here we can actually do something stronger because they're all overestimates. So the best estimate is always the smallest one. So we're going to return the min. Okay. And your min is going to be bad only if all of them are bad. Right? That's stronger than saying it's bad on average. Only if every single one is bad. And what are the odds they're all bad? Yeah, 1 over 2 to the d. Okay. All right, now if I choose d to be log n or something, 10 log n, oops, 1 over 2 to the d becomes 1 over n to the 10. Yeah, so throw some constant in front of your log n, and that constant appears in the exponent, right? Double it, and it goes down like squares the probability, right? So that's a very favorable trade-off for us. And now, if our goal is to ensure all the elements are correct, we can just apply the union bound like we did last class. The probability that any element is bad. We sum up, what's going on? The sum up over all elements, the probability that that element is bad. Yeah, like 1 over 2, or no, n times 1 over n to the 10, because there's n elements, 1 over n to the 10, and you get 1 over n to the 9. N is the number of keys. So you're only using space proportional to the logarithm of the number of possible keys out there, which is like the number of bits anyway. Okay? And you're getting it down to, say, 1 over n to the 9. You could change that 9 very easily by making that constant in front of the log n bigger. Good. So that should be magical. If you haven't seen it before, because all put together, you're able to estimate the relative frequency of every single element up to error epsilon in log n over epsilon space. Yeah, this should be like a miracle result. But what's going on is that that margin of error epsilon does a lot of work for us because it means I only have to worry about a small number of true things. And I can just try to spread out the conflicts. So hopefully I'll isolate them sometimes. Right? And then, I don't see how you can do this without randomization either. Okay, so it's also a nice example of how randomization and approximation lets you do things that are very practical, but might otherwise seem impossible. So I leave this as a homework problem normally in the randomized class, but we can discuss it out loud. We're over time, so you can also leave. So given this kind of data structure, now suppose you want to actually report the heavy hitters. So let me make this more precise. I'll give you a parameter epsilon, okay? And I want you to be able to report a list that includes all the heavy hitters, and you're also allowed to make a mistake and include some epsilon over 2 heavy hitters. Yeah, so I want you to make a list that, if these are like in descending order of and here's like the epsilon mark, I want you to return a list that includes everything that's at least epsilon, but you're allowed to make some mistakes by including a few elements that are at least epsilon over 2. So that's our kind of funny approximation criteria. I definitely want you to make sure you include this, and you can include a few extra, but they should be pretty good heavy hitters, say within a factor of 2. I could have made this 1/2 closer to epsilon, but 1/2 is enough to explore. So how can we use this data structure to try to basically keep track of all the epsilon heavy hitters, allowing for a few extra almost heavy hitters? If the heavy hitter appears at the beginning. Okay, so the elements come in one at a time. What are you going to do? Okay, first element. So we'll initialize the table. First, though, you have to choose your epsilon parameter. Do you want to use the same epsilon? Okay, let's say we use the same epsilon. So you create all these rows and all these columns. First element comes in, you map it, you get the counter. You can even look at the numbers that are left. Then what? Okay, first element you should probably take right away. At that moment in time, it's a heavy hitter. Second element comes in. Yeah, so you kind of keep going. Now the 1 millionth element comes in, you increase the counters, then what? Yeah, there's something like that. Or you can like, how long the stream has been so far. You could check to see if the count is at least an epsilon fraction of the stream. Yeah, so as you increase your table, you can just like remember all the elements where the reported counter is at least an epsilon fraction of the whole stream so far, right? And you can prune it from time to time as the stream gets bigger. That's fine. And then you end up with a list of elements, all of whom have a counted value, at least epsilon fraction of the stream. But is that going to work? So that will definitely include all of the good ones. But what about the almost good and bad ones? Huh? No, they can get replaced often, right? The total number of distinct heavy hitters over the whole stream could be a lot. I don't know, the first 10 appear, you save them, and then the next 20 will be a different pair. Um, maybe. I think you're gonna pay. No, I think there's another issue, but let's say you did, then what? You only get one pass through a stream. But they're estimated frequencies. The issue right now is that you're gonna actually get epsilon error, right? Do you want to change that table's parameter from epsilon to epsilon over 2? So epsilon over 2 additive error will make sure that only these guys are going to get bumped up and nothing below. Okay, so in this sort of approximation where I want to make sure I'm allowed to have some almost heavy hitters, but nothing below that, I want to make my error parameter a little bit smaller, go from epsilon to epsilon over 2. So that's the maximum amount I can add to anything. That makes sense? That was the main issue. That's all. Okay, good. So that's it for hashing and heavy hitters, and me and Ryan are here.